There is a glaring paradox sitting on millions of rooftops right now, and it comes down to a single number: 20%. That is the absolute best efficiency your standard hyper-engineered silicon solar panel can achieve on a good day. For every 1,000 watts of raw solar energy pouring down from the sky onto your roof, an expensive photovoltaic array throws away 800 watts as useless ambient heat just to squeeze out 200 watts of electricity. We have been conditioned to accept this 20% baseline as the absolute pinnacle of high-tech green living. We buy multi-thousand-dollar inverters, lithium battery banks, and complex net metering setups just to manage that tiny sliver of power. But what if I told you that decades ago, a major industrialized nation bypassed the electronics entirely and deployed a system that converts a massive 70% of sunlight into direct usable home energy? Not 20%, not 25%. 70% efficiency. This system requires absolutely zero electricity to run. It has zero moving parts to wear out, zero circuit boards to fry, and zero connection to the local utility grid. Even better, the total cost to build a functional residential unit is less than $100 in raw materials. This isn't a theoretical laboratory prototype or an unproven internet DIY concept. Japan built and installed over 4 million of these exact systems. For decades, families across the country had a continuous supply of free hot water every single morning, every evening, and through every season. In fact, some of those original units installed during the initial boom are still bolted to rooftops today. The components are weathered, the mounting brackets are rusted, but the water inside them still gets incredibly hot. The fundamental physics of the system hasn't degraded by even a fraction of a percent. Yet, despite this flawless mechanical record, Japan practically stopped building them. New installations abruptly collapsed to less than 1/10 of their historical peak. An entire domestic manufacturing and plumbing industry that once served millions of active households essentially vanished overnight. As we dig into the engineering data, it becomes immediately clear that this collapse had absolutely nothing to do with how the technology performed. The mechanism behind this 70% efficiency loop is shockingly simple, rooted in a branch of thermodynamics that modern residential architecture completely ignores. While a standard high-voltage AC compressor works frantically to pump heat out of or into a home, consuming thousands of kilowatt hours and racking up massive utility bills, this passive system uses the house itself as a thermal battery. It turns the natural daily cycle of solar radiation into an automated fluid pump, operating purely on the relationship between fluid density and gravity. In this video series, we are going to break down the exact thermodynamics of this forgotten engineering marvel. I am going to show you the precise mathematical reason why direct thermal conversion beats electrical conversion every single time when it comes to managing a home's thermal load. We will look at the real-world data from the peak of the Japanese solar boom, analyze the fluid dynamics that allow a system to pump its own mass without a mechanical motor, and expose the external economic and structural forces that killed the industry. Most importantly, I am going to show you the exact blueprint and physics principles needed to replicate this ultra-high efficiency thermal loop yourself for under $100, allowing you to cut your home's energy footprint using nothing but raw sunlight and basic geometry. To truly understand how a system can achieve 70% thermal efficiency with zero moving parts, we have to look at the house through the lens of pure thermodynamics. In modern residential engineering, we treat heat as an active enemy to be fought off with brute force mechanical power. We install multi-ton, power-hungry air conditioning units and high-voltage electric water heaters that consume thousands of watts of electricity every single hour. But if you strip away the high-tech electronics, a house is nothing more than a thermal container, a specialized thermos. And the single most inefficient thing you can do in engineering is convert high-grade kinetic or electrical energy into basic, low-grade thermal energy when the environment is already offering you that thermal energy for free. The physics behind this 70% conversion loop relies on two foundational principles: direct blackbody radiation absorption and thermosiphon fluid dynamics. When we look at a standard photovoltaic solar panel, the silicon cells must absorb a photon of light and use its energy to knock an electron free, creating an electrical current. This quantum process is inherently limited by the Shockley-Queisser limit, which caps single-junction silicon efficiency at around 30% in perfect lab conditions, and closer to 18 to 22% in the real world. The rest of that incoming solar energy is completely wasted. It simply excites the atoms in the panel, turning into ambient heat that actually lowers the panel's electrical efficiency. A solar thermal system, however, cuts out the middleman entirely. It doesn't want electricity. It wants heat. When sunlight hits a dark, specialized absorber plate, the molecules in that plate absorb the entire spectrum of solar radiation, not just a specific band of visible light, but the infrared and ultraviolet spectrums as well. This causes immediate, violent molecular vibration, turning radiation directly into thermal energy. Instead of discarding the heat as waste, the thermal collector captures it. Because you are not trying to force a quantum electronic transition, your conversion efficiency immediately leaps from 20% to anywhere between 65% and 80%. The real engineering challenge isn't capturing the heat, it's keeping it up and then moving it into the home without using an electric pump. To solve the insulation problem, engineers developed two distinct collector designs: the flat plate collector and the evacuated glass tube. A flat plate collector acts exactly like a heavy-duty greenhouse. It features a solid sheet of copper or aluminum coated with a selective surface material, usually a chemically bonded layer of black chrome or blue titanium oxide. This coating is engineered with highly specific optical properties. It has an absorptance rating of over 95% for short-wave solar radiation, but an emittance rating of less than 5% for long-wave infrared heat. This means the plate is a thermal sponge. It sucks in almost all the light that hits it, but it physically cannot radiate that heat back out into the air. Tubes are welded directly to the back of this plate, carrying water or a heat transfer fluid like propylene glycol. To prevent the surrounding air from stealing this heat via conduction, the plate is encased in an insulated box with a sheet of low iron-tempered glass on top. The glass allows the high-energy solar radiation to pass through cleanly, but traps the longer wavelength heat waves bouncing off the plate inside the box. Evacuated tube collectors take this insulation to the absolute physical limit by utilizing the best insulator known to science, a vacuum. Each tube consists of two concentric cylinders of borosilicate glass, which is incredibly tough and highly transparent. The air between the outer glass tube and the inner glass tube is mechanically sucked out, creating a permanent hard vacuum with a pressure lower than 0.001 pascals. Because a vacuum contains no air molecules, it completely eliminates two of the three methods of heat transfer: conduction and convection. Heat cannot travel through a medium that isn't there. Inside the inner glass tube sits a copper heat pipe containing a tiny amount of specialized fluid, typically distilled water mixed with an alcohol-based surfactant under a partial vacuum. Because the internal pressure inside the copper tube is incredibly low, the boiling point of this fluid drops significantly. When the sun hits the selective coating on the inner glass tube, the copper pipe heats up. Even at an ambient winter temperature of 32 Fahrenheit or 0 degrees Celsius, the fluid inside the copper pipe begins to boil and vaporize at just 77 Fahrenheit or 25 degrees Celsius. This vapor immediately rushes upward to the top of the tube, entering a copper bulb called the condenser. The condenser is plugged directly into an insulated horizontal manifold at the top of the array, through which domestic water flows. As the hot vapor hits the cooler condenser bulb, it transfers its latent heat of vaporization directly into the domestic water supply. The vapor cools, condenses back into a liquid, and flows back down the tube via gravity to repeat the cycle. This phase change loop allows an evacuated tube system to safely heat water to 140 Fahrenheit or 60 degrees Celsius even under heavy cloud cover or in sub-zero alpine conditions. But how do we move this heated water into a storage tank inside the house without a circulating pump? The answer lies in the fluid dynamics of thermosiphon circulation, a self-correcting loop driven entirely by gravity and thermal expansion. Water is a fluid that changes its physical density based on its temperature state. At a standard cold utility input temperature of 50 Fahrenheit or 10 degrees Celsius, water molecules are tightly packed, giving it a mass density of approximately 999.7 kilograms per cubic meter. However, as that water absorbs thermal energy inside the solar collector and heats up to 140 Fahrenheit or 60 degrees Celsius, the molecules expand and move apart. This thermal expansion lowers the density of the hot water to approximately 983.2 kilograms per cubic meter. This density differential creates a natural buoyant force. If you position the insulated water storage tank physically higher than the solar collector panels on the roof, gravity will naturally pull the heavier, denser cold water down from the bottom of the tank through a downcomer pipe and force it into the bottom inlet of the solar collector. As this cold water pushes its way into the collector's internal channels, it absorbs the intense thermal energy trapped by the selective coating. The water heats up, expands, and becomes lightweight. The heavy cold water entering from below continually displaces this lighter hot water, forcing it to rise naturally through the collector tubes and up an insulated riser pipe directly into the top of the storage tank. This is a beautiful, self-regulating thermodynamic engine. The speed of the water flow is directly proportional to the intensity of the sun. On a blazing hot summer day with high solar irradiance, the temperature gap between the collector and the tank widens rapidly. This maximizes the density difference, causing the water to circulate at high velocity, moving maximum BTUs of heat out of the collector and into the thermal battery of the tank. On a cloudy afternoon, the temperature gap shrinks, the density differential drops, and the circulation naturally slows down to a crawl. The system effectively possesses an automated variable speed pump, but without a single wire, sensor, motor, or kilowatt of electricity. Let's look at the hard operational numbers that define this system under real-world conditions. A standard residential installation utilizes a collector array with an active surface area of 3 square meters and a 200-liter insulated storage tank. In areas with decent solar exposure, the average daily solar irradiance is roughly 1,000 watts per square meter at peak sun. With a 70% efficient thermal loop, that 3 square meter collector is actively dumping 2.1 kilowatts of continuous thermal energy directly into the water tank. To calculate exactly what this means for a household, we use the specific heat capacity formula: energy equals mass times specific heat times delta T. Water has an incredibly high specific heat capacity of 4.184 joules per gram per degree Celsius. To raise the temperature of that 200-liter tank from a cold groundwater baseline of 50 Fahrenheit or 10 degrees Celsius up to a scalding shower temperature of 140 Fahrenheit or 60 degrees Celsius, you need to achieve a temperature lift, a delta T, of 50 degrees Celsius. Plugging the numbers into the equation shows that this thermal lift requires roughly 41.8 megajoules of total energy, which converts to approximately 11.6 kilowatt hours of heat. Because our passive 3 square meter collector array is generating 2.1 kilowatts of thermal power at peak sun, it will take the system just 5.5 hours of clear sunlight to completely heat the entire 200-liter tank from scratch. For a standard family of 4, 200 liters of hot water covers 100% of their daily shower, dishwashing, and laundry needs in a conventional grid-tied home, generating that 11.6 kilowatt hours of daily thermal energy. Using a standard electric resistance water heater requires pulling exactly 11.6 kilowatt hours of high voltage juice directly from the utility grid every single day. Over the course of a full year, that amounts to over 4,200 kilowatt hours of electricity dedicated solely to heating water. If your local utility grid charges a standard rate of 15 cents per kilowatt hour, your family is burning over $630 a year just to take warm showers. The passive solar thermal loop completely deletes this entire baseline expense from your household ledger using nothing but basic fluid density changes and gravitational pull by utilizing the thermal mass of the water itself as a cold battery during the night and a heat sink during the day. This system stabilizes the home's macro energy dynamic. It acts as a mechanical buffer, soaking up the brutal thermal spikes of midday solar radiation that would otherwise overheat a roof, and locking that energy safely inside a heavily insulated tank for later use. This is thermodynamics at its most direct, an elegant manifestation of natural law that completely bypasses the fragile, high-cost supply chains of modern electronics manufacturing. Building a passive solar thermal water heater that delivers up to 70% thermal efficiency does not require access to high-tech industrial supply chains or cleanroom manufacturing. It requires a precise understanding of material science, fluid dynamics, and geometric alignment. You can assemble a rugged, low-maintenance flat-plate thermosiphon loop using standard off-the-shelf plumbing components and raw materials for under $100. This build log will detail the exact step-by-step logic, material dimensions, and physical layout required to successfully build a fully functional system while steering clear of critical engineering mistakes that cause passive thermal loops to fail. The entire system breaks down into 3 core assemblies: the collector box, the absorber plate manifold, and the elevated thermal battery tank. To build the collector box, You need a rigid, weather-resistant outer housing to contain the heat and protect the internal components from ambient wind currents. Source a sheet of exterior-grade 1-2-inch plywood and cut a backing plate measuring exactly 3 feet by 6 feet, providing roughly 18 square feet or 1.67 square meters of surface area. Frame the perimeter of this backing plate with 2x4 lumber to create a shallow, open-faced wooden box with an interior depth of 3.5 inches. Before placing any metal inside this box, you must install a high-efficiency thermal barrier to prevent conduction losses into the wood framing. Line the bottom and interior sidewalls of the box with 1.5-inch thick rigid polyisocyanurate foam board insulation. Polyisocyanurate is chosen because it maintains structural integrity at high temperatures, resisting thermal degradation up to 300 Fahrenheit or 149 degrees Celsius, and offers an excellent thermal resistance of R9. Cover the face of the foam insulation with a layer of heavy-duty aluminum foil to act as a radiant barrier, reflecting infrared heat waves back upward into the collector zone. The core of the system is the absorber plate manifold, where radiation is captured and transferred to the fluid. You will need a solid sheet of 26-gauge flashing copper or, as a lower-cost alternative, a 0.040-inch thick aluminum sheet cut to fit tightly inside the insulated box cavity. Paint the front face of this metal sheet using a specialized high-temperature ultra-flat black coating. Do not use standard glossy spray paint. Glossy finishes reflect high-energy visible light waves. Use a dedicated solar-selective paint or a flat black engine manifold paint rated to 2000 Fahrenheit or 1093 degrees Celsius, which maximizes shortwave absorption while minimizing infrared emittance. For the fluid channels, avoid plastic PEX tubing entirely. PEX is an excellent insulator with a low thermal conductivity of roughly 0.51 watts per meter Kelvin, meaning heat cannot efficiently pass through the pipe wall into the water. Instead, use rigid, half-inch Type M copper pipe which possesses a massive thermal conductivity of approximately 401 watts per meter Kelvin. You will lay out a parallel grid manifold, often called a riser and header configuration. Cut 2 pieces of 3/4-inch copper pipe to a length of 34 inches to serve as your main horizontal headers. Next, cut 6 pieces of 1/2-inch copper pipe to a length of 68 inches to act as your vertical risers. Using a drill press and a step bit, drill 6 half-inch holes spaced precisely 5.5 inches apart along the sidewalls of both 3/4-inch header pipes. Clean and deburr the edges of all holes and pipe ends using a wire brush and emery cloth. Insert the 6 1/2-inch riser pipes into the corresponding holes of the 2 horizontal headers. Creating a ladder formation, lay a generous layer of lead-free plumbing flux to every joint. Using a propane or MAP-P gas torch and lead-free plumbing solder, heat each junction until the solder flows smoothly into the gaps via capillary action. Once completed, pressure test the entire copper ladder to 60 psi using a basic air compressor and a pressure gauge to ensure there are 0 pinhole leaks. Now, you must thermally bond this copper ladder to the flat metal absorber sheet. This is the single most critical step where many amateur DIY builders fail. Simply strapping the pipes to the sheet creates a microscopic air gap that acts as a thermal block, slashing your conversion efficiency by more than half. To achieve proper conductive heat transfer, lay the flat black metal sheet face down. Position the copper ladder manifold on top of it. Use heavy-duty, zinc-plated pipe straps to mechanically clamp the 1/2-inch vertical risers flat against the metal sheet every 12 inches, securing them with self-tapping screws. Next, pack the entire seam where the copper pipe contours touch the metal plate with high-conductivity thermal paste or a specialized aluminum-filled epoxy. This ensures a 100% solid thermal bridge, allowing heat absorbed by the large flat plate to conduct instantaneously into the copper pipe walls. Flip the completed plate assembly over and drop it into the insulated wooden box so that it rests squarely on top of the radiant foil barrier. The 2 3/4-inch main headers should protrude cleanly through pre-drilled holes in the sides of the wooden box frame. To seal the box and lock in the heat via the greenhouse effect, cap the front face with a sheet of 1/8-inch clear, low iron tempered glass or high-grade UV-stabilized polycarbonate. Secure the glazing panel with a rubber gasket around the perimeter and screw down aluminum retaining angles to make the entire box perfectly airtight and weatherproof. Next is the setup of the elevated thermal battery tank. For a 1.67 square meter collector, a standard 30 to 40 gallon repurposed electric water heater tank or a heavy-duty food-grade steel drum works perfectly. Strip away any damaged factory insulation and wrap the outer tank walls in a minimum of 3 inches of rock wool insulation or fiberglass batting, securing it with heavy strapping. This insulation layer must be completely airtight. If the tank loses heat to the night air, your stored hot water will cool down before morning. Now comes the vital geometry of the thermosiphon installation. The water storage tank must be mounted completely above the highest point of the solar collector box. The vertical distance between the top header of the solar collector and the bottom port of the water tank should be at least 12 inches, though 2 feet is optimal. If you place the tank lower than the collector, or even level with it, the buoyant forces will stall. The water will overheat and boil inside the panel, and the loop will fail to circulate. To plumb the system together, connect the bottom cold water output port of the storage tank to the lower horizontal header inlet of the solar collector box, using an insulated 3/4-inch line. This is your downcomer pipe. Next, connect the upper horizontal header outlet of the solar collector box to the top hot water inlet port of the storage tank, using another insulated 3/4-inch line. This is your riser pipe. Keep these pipe runs as short and straight as possible. Avoid sharp 90-degree elbows. Instead, use 2 45-degree fittings to minimize fluid friction. Every extra foot of pipe and every sharp bend adds hydraulic resistance that can choke the delicate, gravity-driven thermosiphon flow. When firing up the system for the first time, you must watch out for beginner pitfalls. The #1 killer of a new thermosiphon loop is an airlock. Because the fluid is moving solely due to tiny density differences, a single trapped air bubble at the top of the plumbing line will completely block the flow, causing the system to stall. To prevent this, always install a manual or automatic air release valve at the absolute highest point of the riser pipe where it enters the storage tank. When filling the system with water from the bottom up, open this valve until a steady stream of water escapes, confirming that 100% of the air has been purged from the copper lines. Furthermore, if you live in an environment where ambient winter temperatures drop below 32 Fahrenheit or 0 degrees Celsius, a direct system filled with pure domestic water will freeze, expand, and split the copper riser tubes, destroying your manifold. In these climates, you must convert the design into an indirect closed-loop system. Fill the collector manifold and tank heat exchanger jacket with a non-toxic mixture of 60% distilled water and 40% food-grade propylene glycol, which drops the freezing threshold down to 10 Fahrenheit or 23 degrees Celsius. To test the operational efficiency of your build, install dial thermometers in line on both the downcomer and riser pipes. On a bright, cloudless day with an ambient temperature of 75 Fahrenheit, you should see the cold downcomer temperature sitting around 65 Fahrenheit as it leaves the bottom of the tank. As the fluid passes through the collector plate, you will watch the riser thermometer climb steadily to 135 Fahrenheit or 145 Fahrenheit within minutes of exposure, proving that the passive thermal engine is actively lifting the fluid temperature by 70 degrees entirely through solar absorption and gravitational buoyancy. To validate the real-world viability of this high-efficiency thermal engine, we have to look past modern lab testing and examine how it behaves under severe environmental stresses. When we look at global deployment data, we find that the physics of passive solar thermal collection excels in the most unforgiving climates on Earth. From the scorching, arid expanses of desert regions to freezing, high-altitude off-grid homesteads. And even within complex ancestral infrastructure that functioned seamlessly centuries before the invention of the electric grid. Let's look first at an extreme desert scenario, a remote homestead in the American Southwest or North Africa, where daytime temperatures regularly soar to 113 Fahrenheit or 45 degrees Celsius, but grid power is either non-existent or prohibitively expensive. In these high irradiance zones, a standard photovoltaic solar panel degrades in performance due to a negative temperature coefficient. As the silicon cells heat up past 77 Fahrenheit or 25 degrees Celsius, their electrical efficiency drops by roughly 0.4% for every single degree Celsius of temperature increase. On a blazing desert afternoon, a PV panel's actual output can easily plummet by 25%. A solar thermal system handles these conditions with ease because it thrives on high ambient baselines. In a desert off-grid setup, a standard 2 square meter flat plate collector experiences virtually zero convective heat loss because the delta T between the internal collector plate and the outside air is incredibly narrow. On an average day with a peak solar insolation of 1,100 watts per square meter, The fluid inside a well-bonded copper manifold will hit its target temperature of 158 Fahrenheit or 70 degrees Celsius by 11 in the morning, because the desert floor cools down rapidly at night due to radiative cooling into the clear sky. This system acts as a crucial domestic resource, storing large amounts of thermal mass that can be tapped for hot water throughout the freezing desert nights. Conversely, if we move the system to a sub-zero, high-altitude off-grid environment, such as a homestead in the Rocky Mountains or Northern Europe, the engineering strategy shifts, but the core thermodynamic laws remain identical. Direct flat plate collectors face heavy conductive losses because the outside air temperature might sit at 14 Fahrenheit or 10 degrees Celsius. This is where the evacuated glass tube collector becomes mandatory, because the hard vacuum between the concentric borosilicate glass layers eliminates all molecular conduction and convection. The internal copper heat pipe remains completely isolated from the freezing wind. As long as light passes through the glass, the selective inner coating absorbs the photons. The internal alcohol-based fluid boils at low pressure, transferring heat to the main manifold at 70% efficiency, while the outer glass tube remains completely cold to the touch. This creates a striking temperature differential. It can be mid-January, with snow covering the ground and an ambient temperature well below freezing. Yet the water entering the homestead's internal thermal storage tank is consistently clocked at 122 Fahrenheit or 50 degrees Celsius. The only maintenance requirement in these extreme northern zones is a structural one, mounting the collector array at a steep 60-degree angle, which matches the low winter sun angle and naturally sheds heavy snow loads before they can shade the glass. This harmony with environmental physics isn't a modern breakthrough. It is a direct continuation of ancestral engineering methods developed in arid regions thousands of years ago. If you travel to the ancient desert cities of Iran, such as Yazd, you will find passive thermal management systems that achieve remarkable cooling and water regulation without a single watt of electricity. The core of this historic infrastructure relies on the integration of two structures: the badgir, or traditional wind tower, and the qanat, a vast network of subterranean aqueducts. A badgir is a vertical masonry tower built over a dwelling with specific structural openings at the top to catch passing desert breezes. When a hot wind hits the top of the tower, the air is funneled downward into the structure. However, before this air enters the living spaces, it is routed directly over the opening of a qanat, an underground channel carrying cold snowmelt from distant mountains. Because the earth provides immense thermal mass, the subterranean water channel remains at a constant temperature of roughly 59 Fahrenheit or 15 degrees Celsius year-round. As the hot, dry desert air passes directly over this cold flowing water, two things happen simultaneously. First, sensible heat is rapidly conducted from the air into the earth-sheltered water, dropping the air temperature instantly. Second, the dry air absorbs moisture from the water surface, triggering adiabatic evaporative cooling. The physics of this process is governed by the latent heat of vaporization of water, which requires a massive 2,260 kilojoules of energy to convert just 1 kilogram of liquid water into vapor. This thermal energy is stripped directly from the moving airstream. The resulting air current, now cooled by up to 30 degrees Fahrenheit and optimally humidified, rises naturally into the living quarters due to the pressure differentials created by the building's architecture. Simultaneously, the hot air inside the house rises toward the ceiling and exits through separate exhaust flues in the wind tower via the chimney effect, creating a continuous, self-powered loop of fresh, cool air. Modern passive house engineering takes these exact historical principles and refines them using advanced material metrics. In a high-performance passive house, the entire building envelope is treated as a unified thermal container. Thick walls constructed from high-mass materials like rammed earth, adobe, or heavy stone are designed to exploit thermal lag, the time it takes for heat to conduct through a structural material. In a hot desert climate, a 24-inch thick adobe wall possesses a thermal lag of roughly 10 to 12 hours. This means the brutal heat of the 12 midday sun is absorbed by the outer surface of the wall, but it doesn't reach the interior living space until midnight. When the outside air has dropped to a chill, and the heat is actually welcome, by pairing high thermal mass walls with strategic solar orientation, modern passive design eliminates the structural need for traditional air conditioning. South-facing windows are calculated with precise roof overhangs, In the summer, when the sun is high in the sky, the overhang completely shades the glass, keeping the interior cool. In the winter, when the sun hangs low on the horizon, the sunlight passes underneath the overhang, striking the high-mass concrete or stone floor inside the house. The floor acts as a direct thermal battery, soaking up the heat during the day and radiating it back into the rooms at night. When you link this structural design with a passive solar thermal water heater on the roof, you decouple the home from the centralized industrial energy grid entirely. You are no longer purchasing energy to fight the environment. You are using basic mechanical layout and material science to let the environment balance itself. When you look at the macroeconomics of modern residential energy, the dominance of standard air conditioning and grid-tied electric water heaters makes very little engineering sense. It is the result of a heavily subsidized industrial framework designed to keep households dependent on a continuous utility bill. Consider the direct comparison between a standard high-efficiency air conditioner paired with a photovoltaic array and a purely passive solar thermal system. To run a standard 3-ton AC unit, you need about 3,500 watts of continuous electrical power. To generate that power with 20% efficient solar panels, you need at least 18 to 20 square meters of roof space, a $3,000 hybrid inverter, a $5,000 lithium iron phosphate battery bank, and specialized high-voltage circuit breakers. The payback period for this setup often stretches across 12 to 15 years, and by the time you break even, the complex solid-state electronics in the inverter are nearing their end of life. Now look at the economics of the 70% efficient passive thermal loop. By utilizing direct solar absorption and gravity, a $100 DIY system eliminates the single largest component of your home's electrical base load without a single circuit board. Because it converts light directly to heat at over 3 times the efficiency of a PV panel, it requires only a fraction of the roof footprint, roughly 2 to 4 square meters, to achieve the exact same net energy reduction. If the average household spends $50 a month just to heat water, a $100 passive build pays for itself in exactly 60 days. After that 2-month mark, you are operating on pure, unmetered thermodynamic profit. Scaling this technology up to manage whole house heating and climate control is a straightforward matter of scaling fluid volume and thermal mass. In large-scale passive setups, the roof-mounted collector array is connected to a buried underground thermal storage tank containing 2,000 to 5,000 liters of water, often called a hydronic bank. During peak daylight hours, the high-velocity thermosiphon loop dumps millions of BTUs of thermal energy into this massive fluid battery. At night, when the house begins to cool, this hot water is passively circulated through a grid of PEX tubes embedded directly into a high-mass concrete subfloor. The heat radiates slowly from the floor upward, warming the entire structural envelope evenly, completely eliminating the need for a forced air furnace. However, as engineering educators, we must analyze this technology with strict objectivity. Passive solar thermal systems are not magic, and they possess definitive operational limitations that you must design around. The first limitation is the hard ceiling of ambient solar irradiance. If your region experiences weeks of heavy winter overcast or dense fog, the thermal input will drop below the system's baseline conduction losses. In these scenarios, the system must be paired with a secondary, low-power backup heater, such as a small rocket mass heater or a compact gas booster, to handle the final 10% of the home's thermal load during the darkest weeks of the year. The second major limitation is the risk of stagnation. When a high-efficiency system is fully charged, meaning the storage tank has hit its maximum temperature of 160 Fahrenheit or 71 degrees Celsius, the water can no longer absorb heat from the collector. If the sun continues to beat down on a high-efficiency evacuated tube array, the stagnant fluid inside the copper manifold will quickly spike past its boiling point, creating high-pressure steam that can rupture fittings or blow open pressure relief valves. To prevent this, every large-scale system must be designed with a stagnation protection protocol. This can be a simple mechanical gravity shutter that drops a canvas shade over the glass tubes when the tank hits maximum capacity, or a dedicated heat dump line that redirects excess hot water into an outdoor hot tub, an agricultural greenhouse soil grid, or a radiant cooling loop buried deep in the earth. Ultimately, the vanishing of the solar thermal industry in Japan was not a failure of physics. It was a failure of market design. We traded an incredibly elegant, decentralized technology that ran on sunlight and gravity for a high-tech centralized appliance market that could be monitored, metered, and financed. We allowed smooth-talking, door-to-door sales networks and complex government feed-in tariffs to convince us that energy is only valuable if it passes through a copper wire and an electronic meter first. But as the utility grid grows more fragile and electricity prices continue to climb, the flawless performance of those 4 million Japanese rooftop units stands as absolute proof that a different path is completely viable. You do not need a multi-billion-dollar utility grid to live a comfortable, high-efficiency life. You do not need to pay a corporate monopoly for the privilege of running a hot shower or keeping your home stable in a brutal climate. The sun is still putting down 1,000 watts of raw power per square meter every single day. The laws of fluid density and gravitational buoyancy have not changed by a single fraction of a percent since the 1970s. The engineering blueprint is right here. It is proven, and it is entirely within your hands to build. If you want to stop paying for your utility company's inefficiencies and start engineering your own off-grid passive systems, hit the subscribe button right now. In our next video, we are going to head out to the workshop, fire up the propane torch, and build a full-scale 30-gallon evacuated tube thermosiphon system from scratch, logging the exact temperature curves in real time. Stay safe, keep your systems efficient, and I will see you in the shop.